linear approximations are closely related to this other idea called differentials. Now, differentials is kind of a strange thing when you think about it at first, but you'll see, especially later on, especially in Calc 2, that we do end up using them a lot, Calc 2 and Calc 3. The idea is, right, we know that dy dx is another way of writing f prime of x. So, and we said this isn't a fraction, it's just this limit business. But what if we kind of, sort of play with it like a fraction? In other words, what if we define dy and dx as variables in their own right? All right? So the idea is that I can rewrite this way. So define dx as a variable. Then dy is also a variable. It's dependent on dx, and it's dependent on f prime. So then we can define dy this way. And that's really all we're going to do with it. Like, I'll show you like a little homework, a little problem. But what we really want to do is just sort of start thinking about these as we can think about these as these objects, the differentials, the dx and the dy, sort of as objects on their own, related to the derivative. And so from a point of view of graphing, you can sort of understand these things in this way as well. So if you remember, here's my tangent line, right? And remember how we got this tangent line? We figured out that what the derivative was by looking at x and x plus dx and all that stuff. But we had looked at a secant line that moved into a tangent line. So now let's just look at the tangent line. Remember, we stepped a small amount delta x, right? So this point would be x plus delta x. And somebody called it h, but it's also can be called delta x. So one thing, and this triangle is usually very small. I drew it big here so you can see the difference, okay? So this delta x, what are we going to define this dx as being? We're actually going to define dx as being the same thing as delta x. So dx is the same thing as delta x, but dy is not the same thing as delta y. So first of all, what's delta y? Delta y is the difference between y here and y there. So delta y is going to be f of x plus delta x minus f of x. So graphically, that is here. So this is the point x plus delta x, and then this was the point x. So if I look at this bit here is my delta y, okay? Now, that is going to be the slope of that secant line, is delta y. And as this delta x goes to 0, we actually expect our delta y to go to the tangent line, right? So delta y should go to dy. What's dy on the picture? Dy on the picture is this whole bit. Okay, so dy is given by the slope of the tangent line. So it's this. Okay, so if I want to compute dy, now that I know, remember we use the slopes to determine the derivatives with the definition of the derivative. Now we have derivative rules, so we can use the derivative rules to take the derivative and then we can kind of think about dy in those terms. Okay, so in other words, to find the dy, I just used this, f prime of x dx. So this is delta y, and I'll write it down here. dy is f prime of x dx. Okay. We'll just leave that right there, and I'm going to do an example where we find the dy, the delta y, the dx. They tell you what the x and the dx are. So they give you a function. Here's a function. And they ask you to find dy and delta y x is 2 and dx is I'm going to write it here. Dx is 0.05. So again, the dx is always like a small increment. So all I got to do is compute these things, right? dy is f primed of x dx, right? F primed here is going to be x minus 1 squared. So x minus 1 times the derivative of the top, which is 1, minus x plus 1 times the derivative of the bottom, which is 1. So these x's cancel out. I get minus 2 over x minus 1 squared. Okay. So what I want to do, my x is 2, my dx is 0.05, so I just put that in there. Is going to be f primed of 2 times 0.05. So if I put in 2 there, I get 2 minus 1 is 1, so minus 2 times 0.05, right? So there we have. This is just minus negative 0.1. Okay, and that is going to be, if I drew a picture, it would be similar to this, but it wouldn't be the same because you see one point is that this is negative. Okay, so my picture, it must be going down, right? So whereas I drew this, this one was going up, you can draw the same picture with something going down, right? Meaning the function itself going down. So I should have drawn a picture. We didn't draw a picture. Okay, so that's dy. Now what about the delta y? Delta y is f at x plus delta x. So that would be f of 2.05 minus f of 2, right? And if I work that out, 2.05 in here, I've got 3.05 over 1.05 minus 2 in here is going to be 3. Okay, so this ends up being not quite 0.01, but pretty close. 0.0952. But the way these are related to the linear approximation is basically, you see we've got the linear approximation here, that's the tangent line, and we're looking at how dy and delta y and all are related to the tangent line. If I write down my linear approximation, right, it was this. Now I just want to think about slightly differently, right? I want to think about, that's because the variables are different, right? But this is just going to be a small difference, right? So essentially, in terms of differentials, this thing actually ends up being your dy. And it's a little bit confusing because the x there corresponds to the a here. And the dx is going to be that difference between the 2 points. Okay, so, but if you want to think about the linear approximation in terms of differentials, it's like this. Or you can just think about the linear approximation as it is, as a tangent line approximation. So that's actually probably, that's the way I think about it. But, you know, they are related in this way.